Modern software infrastructure relies on interconnected libraries. When a single central node is compromised, it sends a pulse through the entire network structure nodes every week. The immediate blast radius is extensive. Currently, 174,000 downstream projects trust and execute code supplied by this single library. This autopsy examines the specific progression of the exploit, detailing how an attacker bypassed static scanners to deliver a remote access Trojan by targeting execution metadata rather than source code. At this scale, a single point of failure at the top of a dependency tree grants an attacker execution privileges across hundreds of thousands of local and enterprise environments.
The entry vector relied on the theft of a lead maintainer's long-lived classic NPM access token, which granted the attacker complete publishing authority over the repository. To secure this access, the attacker immediately updated the maintainer's account email address to ifstopper.mme. 18 hours before the injection, the attacker deployed a clean file to establish a baseline in the registry. They then pushed poisoned updates to branches 1.14.1 and 0.30.4 via the NPM command line interface, injecting code directly and bypassing standard automated integration guardrails. To avoid detection during manual inspection, the attacker left all 86 core source files of the Axios library untouched. Here is the injection point. The left source code remains clean. On the right, a single dependency was added to package.json, disguised as crypto.js. By targeting execution metadata rather than modifying the source code itself, the attacker ensured that traditional static code review and pull request audits would find no malicious changes to the library's logic. The exploit's execution trigger lives within that modified package.json file, utilizing a native post-install script. The post-install command executes automatically and silently the moment a user or pipeline runs npm install to pull down the library. Once triggered, this script acts as a payload mechanism, calling a hidden dropper file named setup.js into the local environment. The setup.js file defeats static scanning through dual-layer obfuscation. It masks its logic with an XOR encryption keyed to 7077, followed by a base64 encoding layer. The true execution logic is only revealed dynamically in memory, keeping the static text looking like harmless math. Combining native pre-execution scripts with runtime obfuscation creates a structural blind spot where malicious logic executes before the developer ever interacts with the project. Once deobfuscated, the script's first action is to query the host machine to detect its specific operating system architecture. The script contacts an attacker-operated command and control server, which returns a remote access Trojan tailored to the detected Mac, Windows, or Linux environment. This entire sequence, from npm install to complete Trojan delivery, takes exactly 1.1 seconds. Immediately after the initial deployment finishes, the automated cleanup routine initiates by rapidly scrubbing the setup.js dropper file from existence entirely. Next, it deletes the poisoned package.json file from the local directory. Finally, it renames the clean, pre-staged package.md file back to package.json, restoring the environment to its original state. Because the exploit removes its own infrastructure, post-incident local forensics will find no static trace of the files on the disk, making detection nearly impossible once the process finishes. To verify if your systems were exposed, you must run this diagnostic protocol. Use the global command npm list-g Axios to scan your environment for the library. You are looking for the poisoned version branches, 1.14.1 and 0.30.4. Finding either indicates an active compromise. If infected, standard patching or rollback protocols are insufficient. The Remote Access Trojan provides systemic, persistent access to your system. You must isolate the hardware and execute a total rotation of all environment variables, access tokens, and API keys. This exploit succeeded by weaponizing the trust models embedded in open-source registries. Securing modern infrastructure requires a zero-trust approach that audits not just the code we write, but the automated tools and dependencies that assemble it.